MBA633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this segment, we'll develop a confidence interval for the difference between two population means when the population standard deviations are unknown. So sigmas are unknown for the two populations. The problem setting we have is the following. A new bumper is installed on selected vehicles in a corporate fleet. During a one-year test period, 12 vehicles with the new bumper were involved in accidents, incurring a mean damage of 1,101 with a standard deviation of 696. And then 9 vehicles with the old bumpers were involved in accidents, incurring a mean damage of 1766 with a standard deviation of 838. You may recall from a previous video clip that we had used exactly the same problem setting to do a hypothesis test for the difference between two population means. I have retained that problem description, but I've just put a strike through it. And in that case, the problem we had addressed was, did the new bumper significantly reduce damage at the 5% level of significance? That's the hypothesis test we had done. This time around, we want to develop a confidence interval, a 95% confidence interval for mu n minus mu l. So n, the subscript n, refers to cars with the new bumper, and the subscript l refers to cars with the old bumper. So we want to develop a 95 confidence interval for mu n minus mu l. That's the average damage incurred by cars with the new bumper, and mu l is the average damage incurred by cars with the old bumper. So you remember the basic approach to doing confidence interval. We first compute the sample statistic and then we bracket it with a margin of error. So the confidence interval calculation process essentially consists of computing a sample statistic, sample stat, and then we bracket it with a margin of error, so plus or minus margin of error. So what is the sample statistic to be used in this case? Obviously, since we are doing a confidence interval for the difference between two population means, we will use the difference between the two sample means. So x bar n minus x bar l, based on the sample data given to us, is 1101 minus 1766 is minus $665. That's the sample statistic. And now we must bracket that with a margin of error. And the margin of error has to be large enough so that I'm 95% sure of including the unknown parameter difference. So coming back to our sampling distribution, the basis of the quantification of uncertainty is the sampling distribution, as you know. The sampling distribution of x bar n minus x bar l would be a t distribution in this case because the population standard deviations are unknown. And every t distribution has a certain number of degrees of freedom. In this case, you may recall from the hypothesis test problem that we had solved, the degrees of freedom is solved using this little complex formula over here, and it had turned out to be 16, so 16 degrees of freedom. So the sample statistic x bar n minus x bar l has a t distribution with 16 degrees of freedom. And now I want to know how large my margin of error needs to be. So obviously my margin of error needs to be large enough such that this yellow shaded portion that I have, in other words, the sample statistic plus the margin of error, which is the upper limit, and the sample statistic minus the margin of error, which is the lower limit. So the area between L and U has to be 95%. So how large should that margin of error be? You may recall that the built-in Excel function that we would need to use in this case is the T inverse. So equal to TINV, and the T inverse function requires as a probability the area of the two tails. I want the area between L and U to be 95%. So the area in the two remaining tails is 5%. So I put in 0.5, and degrees of freedom is 16. So it's 2.11, meaning my margin of error has to be 2.11 standard deviations wide if I want to be 95% certain of including the true but unknown difference in population parameters. Now obviously now we got to do the next step, is how much is one standard deviation. So you again remember from the hypothesis testing problem that we solved here, the standard deviation of the sample statistic, in this case sigma of x bar n minus x bar l, is given by this expression here, and you can see the two populations showing up in their respective samples, N and L, that's the set of cars with the new bumpers, and L representing cars with the old bumpers. So you have s squared n divided by the sample size of n plus s squared l divided by the sample size of l. Sum them up and take the square root. That comes to $344 when you do the math. What that means is the standard deviation of the sample statistic, the standard deviation of x bar n minus x bar l, is $344. Hence, my margin of error in dollars needs to be 2.12 multiplied by 344. Okay, so that's what my margin of error needs to be. So let me do that calculation and see what that ends up being. Is equal to 2.12 times 344. So it's $729 dollars. So let's say approximately $730. So what is my net result for the confidence interval? So I am 95% sure that mu n minus mu l lies between the sample statistic, which is minus 665, plus or minus the margin of error. Okay, so that's the upper limit and lower limit, or you can rewrite this as, let's see, minus, if we add up 665 and 730, that would be 1395 minus 1395 on one hand, and that's the lower limit of the confidence interval. Let's see what the upper limit would be. So it would be 35 plus 30 is 65. Okay, so I'm 95% sure that the difference between mu n minus mu l lies between minus 1395 to 65. Interestingly, notice that this range includes the value 0. Okay, so at the 95% confidence, you can see that the interval includes 0. So if you had a hypothesis test which said that is there any significant difference between the accident damage for the new and old bumpers, then you would have to conclude that there is no significant difference. But the hypothesis test that we had done was somewhat different. The alternate hypothesis was different if you go back and look at that video. Anyway, for this confidence interval calculation, you can see the logic is pretty much the same as for the single population case. You look at the sample statistic, then figure out how large your margin of error has to be based on your level of confidence. The larger the level of confidence, the larger the margin of error. And then you bracket the sample statistic on both sides by the margin of error and come up with the lower limit and upper limit for the confidence interval. The only difference between the one population case and the two population case is that the expression for the standard deviation of the sample statistic and the degrees of freedom is a little more involved. That's all. Otherwise, the logic remains exactly the same. So don't let the more complex arithmetic get in the way of thinking. The thinking is exactly the same as what you would do for developing the confidence interval for a single population mean.